So this topic is within the topic of counting techniques. Counting techniques. So here we're going to look at what's called the generalized fundamental principle of counting. The generalized fundamental principle of counting. All right, so let's take a look. What is it? So we need a quick definition of what it is. It says that if a task can be completed in K stages and stage I has what we'll call N sub I outcomes, regardless of the outcomes of the previous stages, then the task has N sub 1, N sub 2, all the way up through N sub K outcomes. So let's look at some example. So for each of the following tasks, we're going to specify the stages, the number of outcomes of each stage, and the number of outcomes of the task. So for this example, I'm going to say let's select a plumber. Let's select an electrician. And let's also select a remodeler. And we're going to select a plumber, electrician, and remodeler from this count of 3 plumbers. We have 2 electricians there to choose from. And then we have 4 remodelers. Right, so these are maybe available in the online yellow pages or something. So we're going to select a plumber, electrician, and a remodeler from 3 plumbers, 2 electricians, and 4 remodelers available in the online yellow pages. So this task consists of 3 stages, right? It has 3 stages with the number of outcomes. N sub 1 equals 3, N sub 2 equals 2, and N sub 3 equals 4. Right, these are the amount of outcomes, 2, 3, 2, and 4, as you can see from the problem. So we can easily say that the task has, quite simply, 3 times 2 times 4, which is 24 outcomes. All right, let's go to another where we're told that we want to form this binary sequence. So we're told to form a binary sequence of length 10. Of length 10. So what does that mean? So let's write a little description. So i.e. a 10 long sequence of zeros and ones. That's what we mean. Okay, so this is our next example. So here, the task consists of 10 stages. Task consists of 10 stages. So each stage has 2 possible outcomes for each stage, either what, 0 or 1. So therefore that tells us, excuse me, that the task has 2 raised to the 10th power, which is, punch that in the calculator, 1024 outcomes. 1024 outcomes. Okay, next example. Let's say we're looking to form a string of 7 characters. We're forming a string of 7 characters such that the first 3 are letters. 7 characters such that the first 3 are going to be letters. And also such that the last 4 are going to be numbers. All right, so for this one, the task consists of 7 stages. 7 stages, as we can see. Each of the first 3 stages, right? Each of the first 3 stages involves selecting one of the 26 letters, right? One of the 26 letters. So basically n sub 1 is equal to n sub 2 is equal to n sub 3, which is 26. All right, each of the last 4 stages, according to our problem, involves selecting one of the 10 numbers. One of the 10 numbers. So n4 is equal to, and so on, n sub 7 is equal to 10. All right, so therefore, from that information, we know that the task has 26 to the 3rd power times 10 to the 4th power. So you just compute that in your calculator. It looks like I get 175,760,000 outcomes. All right, so for those examples, we specified the stages, the number of outcomes of each stage, and then the number of outcomes of the task. Now we're at our definition. Our definition says that if the k stages of a task involve sampling 1 unit each without replacement from the same group of n units, then 1, if a distinction is made between the outcomes of the stages, we say that the outcomes are ordered. Otherwise, we say that the outcomes are unordered. All right, and then 2, the ordered outcomes are called permutations of k units. So the number of permutations of k units selected from a group of n units is denoted by the following. And then 3, the unordered outcomes are called combinations of k units. The number of combinations of k units selected from a group of n units is denoted by the following. So permutations and combinations, the formula for the p sub k comma n, that really follows readily from the generalized fundamental principle of counting. So the number of permutations of k units selected from n is going to be for us p k n is equal to n minus 1 n minus k plus 1, which for us we can make n factorial over n minus k factorial. All right, so here we are. N factorial over n minus k factorial. For for a non-negative integer m, the notation m factorial. So let's look at what that means. For a non-negative integer m, the m factorial is defined as m times m minus 1, and you go all the way down till you get to 2 times 1. Right? So, for instance, what am I saying? If we have 4 factorial, that's going to be 4 times 3 times 2 times 1. So 4 times 3 is 12, times 2 is 24, times 1 is still 24. So this is 4 factorial. All right, and then we want to know by definition, to help us in other problems that we might see. If we ever get 0 factorial, by definition that yields 1. All right, so this is what we're gonna have to use. Number of permutations of k units selected from n. All right, and then we want to say that the number of permutations, and then this is of n units among themselves. Of n units among themselves. So this is going to be p sub n comma n is n factorial. All right, another formula for us. So our example is going to be the lineup, right? In baseball, lineup or the batting order. That's going to be a list of 9 baseball players. 9 baseball players in our lineup. It's a list of 9 baseball players for a team in the order that they will bat, right? That's what the batting order is, the lineup is. The list of 9 baseball players for a team in the order that they will bat during that evening's or that day's game. So we want to say, okay, how many different lineups are possible? How many different lineups are possible? Well, for this example, there are P, and we'll use 9 comma 9 based on what we just talked about above. So this is going to be 9 factorial, and there should be a factorial button on your calculator, or if not, you'll just do 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and you should get, I get 362,880 possible lineups. Right? Let's do another example. Let's call that example A, example B. Let's say you have the Department of Transportation. They want to assign 6 civil engineers. 6 civil engineers to oversee some, I guess, 6 civil engineers to oversee. They can oversee 6 highway safety design projects. All right. All right, so the question is, okay, how many different assignments of civil engineers to projects are possible? So how many different assignments of civil engineers, I'll put CEs, civil engineers to projects are possible? All right, well, we'll take P 6 comma 6, it looks like, right? And then we'll just use 6 factorial So that gets me 720 different assignments. 720 different assignments. Okay. So the number of combinations, now, which are unordered selections or groups of k units that can be drawn from a set of n units, that doesn't really follow directly from the generalized fundamental principle of counting, but it does follow from the permutation formulas that I just went over. All right, so if that wasn't clear, make sure you rewind and get that statement that I just said, and make sure you understand what I'm saying. All right, so by the formula that we had, the n factorial over n minus k factorial, the number of permutations of that 3, it could be obtained from a set of 4, right? Would be the formula that we had, where we have 3 obtained from a set of 4. We could go with 4 factorial over 4 minus 3 factorial, right? So what is that going to be? If you write it out, it's just going to be 4 factorial, which is 24. So therefore, the number of combinations of 3 can be obtained from a set of 4 is parentheses 4 over 3, right? The number of combinations of 3 that can be obtained from a set of 4, right? So we have P3 comma 4 over P3 comma 3. So that's 24 over 6, which is 4. So in general, we have the formula, and this is going to be for number of combinations, right? That's what I was talking about, combinations of k units selected from n. So this is going to be n k, and here we have p k comma n over p k comma k. But we can write this formula, and this is the purpose of me doing what I did above to show you how we amount to it. But then we can write the formula as n factorial over k factorial over n minus k factorial. All right, so this is combinations of k units selected from n. All right. So because of the numbers, the n over k in parentheses, k equals 1 all the way up to n, they're using the binomial theorem. They're referred to in some textbooks or online. You might see them referred to as binomial coefficients. Okay, so let's look at our example. Our example says that we have 2 cards being selected from a deck of 52 cards. All right, the question here is, first, how many outcomes are there? Let's write this out. How many outcomes are there if that first card will be given to player 1, and the second card to player 2. Okay, so in this case, it makes sense to distinguish the outcome, right? Ace, king, meaning that player 1 gets the ace and player 2 gets the king from the outcome, we could say king ace. So therefore, we're interested in the number of permutations of 2 cards selected from 52. That's what we're interested in. The permutations of 2 cards selected from 52. So according to the formula that I gave earlier, the number of ordered outcomes is P2 52. Number of permutations of 2 cards selected from 52. So that's just going to be 52 times 51. And that's 2,652. All right. And then let's go ahead with a part B. So let's say our part B says how many outcomes are there if, let's say, both cards will be given to player 1. All right, so how many outcomes are there if both cards will be given to player 1? Well, in this case, it can be argued that the order in which the 2 cards are received is not relevant, since both result in the same 2-card hand, right? It results in the same 2-card hand, so the order doesn't really matter because you're giving it to player 1. So therefore, we're interested in the number of combinations. Here in this part, we're interested in the number of combinations of 2 cards selected from 52 cards, right? That's what we're interested in. The number of combinations of 2 cards selected from 52 cards. So according to the most recent formula that I gave, the number of unordered outcomes is so we have 2,652 divided by 2, right? And then that gives us, what is that, 1,326, right? This is from the NK formula that I just gave earlier, where it had n factorial over k factorial n minus k factorial. So make sure you're doing the correct simplification mathematically, and then you should be able to get 2,652 over 2, which is 1,326.